We are going to dive straight into how we derive the equations of motion. That is motion in a straight line. We have 5 equations of motion, and we are going to, in this video, I'm going to show how we derive the equations of motion. But before we get into the derivations, I would like to take you through the overview of where we are going. To begin with, the parameters we are going to consider are displacement, which is going to be denoted by S. We have the initial velocity, which will be denoted by U. We will have the final velocity, which is denoted by V. Then we will have the acceleration denoted by A, and then the time denoted by small t. Now, what are these equations that we are trying to derive? The equations of motion are basically 5. We have the first equation of motion, which is V is equal to U plus AT. We have this one, we have that one. For displacement, we have this one for V squared is equal to U squared plus 2AS, and then finally that one. But in all these 5 equations, you notice that in each and every equation, there is a certain parameter that is missing. If you look at these parameters that we considered at the beginning, the displacement, the initial velocity, the final velocity, the acceleration, and the time, if you're to examine each and every equation, there is a parameter missing, one parameter of all. If in a certain equation you'll find that all these 4 parameters are there and S is missing, then in another equation you'll find that U is missing and all the other parameters are there, or you'll find T missing and all the other are there, and so on. And so it means that as we are deriving these equations, we have to put in mind in some of our substitutions that there are certain parameters that we will be deliberately leaving out for us to be able to attain the equation we're trying to derive. For example, if you look at the first equation of motion, it is S that is missing. There is no displacement here. But this displacement is in all the rest of these equations. If you look at this second equation, we have A missing. The acceleration is not represented, but acceleration is in all the others. In the third equation, you're having final velocity missing, but final velocity is represented in all the other 3. Then likewise here, time in this equation is missing, but it is represented in all the other equations. And finally, even in this final equation, you're having U missing, but this U is represented in all those other equations. So we'll get started with first coming from where acceleration comes from. Now, acceleration by definition, from our theory, we know that acceleration is the rate of change of velocity. Now, if we are to use an illustration as in our screen diagram below, the write-up says that if an object is to move in a straight line from 5 meters squared, and after 3 seconds its velocity is 11 meters squared, this is what has been illustrated here, that this object starts moving from 5 meters squared. So it means that 5 meters squared is its initial velocity U. Then it moves, and after 3 seconds, so after traveling for 3 seconds, this is from 0, after 3 seconds, its velocity is 11 meters per second. So it means that it moves, and its final velocity here, which is V, is going to be 11 meters per second. Then it means that the object was accelerating. It accelerated from an initial velocity of 5 meters per second to a final velocity of 11. And it means that when we draw this graph of velocity against time, the velocity time graph, when we draw this graph, the gradient of this graph represents the acceleration. And now, to find the gradient, of course, the formula for gradient is going to be change in y. So what is changing in y? The final velocity 11. To get this acceleration, the slope, acceleration is going to be equal to the change in y, which is 11 minus 5. Divide that by the change in x. The change in x, of course, it's the final minus the initial, which is 3 minus 0, giving us 3. 11 minus 5 is 6. Divide that by 3. Now this 11 minus 5, of course, is in meters per second, and this time is in seconds. So 6 over 3 is going to give us 2. Now 2 is in meters per second squared. Of course, this meters per second squared is coming from here. Meters per second divided by second gives us meters per second squared. So now this 2 meters per second has been gotten from the slope of this graph, and this is the acceleration. Acceleration is the rate of change of velocity, because as you can see here, we are having velocity being divided by time. So the rate of change of velocity is what has given us this acceleration. And so we are going to use this kind of analogy to derive our first equation of motion. Now looking at that, our first equation of motion, still we are going to consider an object. It is moving from initial velocity u to final velocity v, and when you draw a velocity time graph, this is velocity in meters per second, this is time in seconds. So to find that slope, we know that right here, the slope of this graph, to get the acceleration, the slope is going to be change in y. Now of course the change in y is the final minus initial, the final velocity v minus the initial velocity, which is u, divide that by the change in x. The change in x, of course, it's the final time, which is t, minus the initial time, which is 0. This is supposed to give us the slope, which so happens to be the acceleration. So when we make this a flat equation, this becomes v minus u over t is going to be equal to a. Multiply t on both sides. This goes with that. You remain with v minus u, giving us a t. When we make v the subject of the formula, v becomes, u goes the other side, u plus a t. Just here, v minus u over t is equal to a, and this step comes to that. This is how we arrive at this, which is that. Now that makes up our first equation of motion. V is equal to u plus at. So now we are going to go on to the next equation of motion. Now still the next equation of motion, we are still going to use this very graph. From our theory, we know that the area under a velocity time graph represents the distance traveled by that particular particle. And in this case, if you look at this graph, if I'm to draw that right there, it is going to form what we call a trapezium. So now the trapezium, it means that if we are to find the area of this trapezium, the area of this trapezium is going to give us the distance traveled by this particle from that point, the distance traveled by this particle from initial velocity u to final velocity v. So the area of a trapezium if we are to change this graph like this, this is how the trapezium looks like. And so it means that as far as our trapezium is concerned, our value of a, the height of the trapezium is going to be that one, this, and this will probably be our value of a, and this is our value of b. And now the area of a trapezium is given by, area of a trapezium is going to be a half h into a plus b. And from our trapezium earlier, I'll redraw it here. Now looking at our trapezium here, if I'm to put it upright, the way it should look like, this is going to be our value of h, and our value of h is definitely coinciding with the length 0 to t, so this is our value of t right there. Then here we are looking at it this way. Then here it is coinciding with u, because from here to there the length is u, initial velocity, so our value of a is corresponding to the value of u, and then our value of b here is corresponding to our value of v, which is v. This is v, this is u, and this is our value of t. And I have extrapolated this and I have put it there like that. So it means from our area it's going to be a half h into a plus b, which is going to be a half times t. Our value of h corresponds to the time into the initial velocity u plus the final velocity, which is v. And definitely when we rearrange this, this becomes u plus v over 2, and all this is times t, which is that one. So this makes up our second equation of motion from that graph. If we are not to use the graph to find the second equation of motion, we can relate it that we know that average velocity is going to be initial velocity plus final velocity, divide that by 2. And also another formula for average velocity is displacement, divide that by time. So it means that we are going to equate this to that. So that's how we end up with displacement over time is equal to average velocity, which is u plus v over 2. So displacement is denoted by s, divide that by time, is equal to u plus v over 2. Then when we make s the subject of the formula, we end up with s is equal to u plus v over 2 times t. And this is just an alternative way, or this is another way we can find our second equation of motion. And so we'll go ahead and derive our third equation of motion. Now, our third equation of motion, we are still going to consider this very graph, but we are going to look at this graph. We are still going to try and find the area under this graph, but only that this time around, the area under this graph, instead of finding the area as a trapezium, we are going to divide this area into two. And so we are going to get the area of this triangle, and we add that area to that rectangle. And then when we add the two areas, we are going to get an expression that is going to give us our next equation of motion, the third equation of motion. So here is how we are going to do it. We are going to get the area under this graph, but we are going to divide it like that. So we have area of A and area of B. And definitely, of course, here, the area of this first portion, our value of A, is going to be a half. This is a triangle, and we know that the formula for finding the area of a triangle is a half times base times height. So that is a half times base times height plus the area of the rectangle, which is length times width. And of course, in this case, it's definitely going to turn out to be that our A, which is the distance, because our area under this graph is the distance, so distance S is going to be a half times base. Now the base here is t, because the distance is t, times height. Now the height here is v minus u. This is v minus u. Where is the v minus u coming from? Of course, v minus u here is the distance from here to here is v. The distance from here to here is u. This is v, this is u. So to get this remaining distance, which is corresponding to that, it's going to be v minus the u to get that remaining distance. That's how we come up with that v minus u plus, now length times width. This is a triangle, a rectangle. Our value of length is, that's our length, which is t, and our width, which is u. So that's how we come up with that step. So from here, it's going to become a half. Now this AT has replaced that into this. So it is a half times v minus u, which is actually this whole thing. This whole thing is that, this whole thing becomes AT squared plus ut. Now how does this come about? Now we know that acceleration is the rate of change of velocity. So we know that acceleration is the rate of change of velocity, and by that we mean that acceleration is going to be equal to, this is the definition of acceleration. Acceleration is the rate of change of velocity. Final velocity minus initial velocity over t. Now when we make this a flat equation and we multiply t on both sides, we shall end up with at going to be equal to v minus u. So you realize that this v minus u, which is here, is the same as 80. So we get this v minus u and replace it with 80. So it means that when we get from this step, let me rewrite it here. When we come from this step, which is a half t into v minus u plus ut, the next step after this is going to become a half times t into v minus u. Now v minus u is the same as 80, so instead we shall write 80 right there plus ut. So now 80 times t becomes a half a t times t is t squared plus ut. So this is how this a half 80 squared plus ut, this is how it comes to be like this in the next step. So now when we get to that, we have formulated our third equation of motion. In this case, our third equation of motion is that one. It shows that s is equal to ut plus a half at squared. That's our third equation of motion. Alternatively, we can find the third equation of motion by substituting. So for us to get our third equation of motion, the fourth equation of motion, and the fifth equation of motion, those other three equations also are going to be derived using substitution. So now the substitution is going to be entirely based on which parameter do we want to eliminate. We eliminate that parameter by substituting the first two equations. Now the first two equations of motion we got were, now these are the first two equations of motion we got. We got this first equation of motion using the graph. We got this second equation of motion also using the graph. When we got this first equation of motion, we were basically depending on the theory that acceleration is equal to the rate of change of velocity. From its definition, from the definition of acceleration, we were able to derive this equation. And then for us to be able to get this second equation of motion, we were able to get it by looking at the area under the graph. So all these other three equations of motion shall be gotten by substituting these two. So it means that if we want to get the value, the third equation of motion, we are simply going to eliminate v in this equation. So we are going to get the value, the expression for v, which is this one, and substitute it here to get this one. If we are going to, for us to get the fourth equation of motion, it means we need to eliminate t. If we are to eliminate t, it means we are going to get this value of t here, make t the subject of the formula in this equation, come and substitute the value of t here, so that we eliminate t in this expression, and that's how we are going to get this expression. Likewise, in the fifth equation of motion, we are eliminating u. So it means we're going to get u here, get this equation, the first equation, make u the subject of the formula, then get the expression for u in this equation, substitute it here, and then we'll be able to get the fifth equation of motion, like that. So you can do it any way you like, but the main idea behind is that we are formulating these equations based on eliminating the parameters that you see right here. So we'll go ahead, dive straight into it. So it means that for us to substitute for to get the next third equation of motion, we are going to get this equation of motion, which is the second equation of motion we derived earlier, and then we eliminate v. When we eliminate v, it means that we are going to eliminate v from our first equation. Our first equation of motion was v is equal to u plus at. And our second equation we got was this one. So we are going to get this value of v and substitute it right there. When we substitute it right there, u plus at is what we put here. So it's going to be u plus v which is equal to u plus at, divide that by 2 times time. And so from there we shall end up with u plus u is 2u, and then plus at, which is 80. And of course, when you multiply this times time, it becomes 2ut, and then 80 times time becomes 80 squared. All this divide by 2. And then that's how we end up with our third equation of motion. So we are going to use the same idea. We're just going to play around with the first equation and the second equation to substitute them to make the fourth equation of motion. Again, our fourth equation of motion, we are going to get our first equation, which is v is equal to u plus at. And when we make t the subject of the formula, it becomes t is equal to v minus u over a. So we are going to get this expression of t and substitute it in the second equation we derived earlier. So we are going to replace this value of t. So when we put this expression here, this value of t has been replaced here. So it's going to be v plus u over 2, then v minus u over that. So when this multiply that becomes u plus v into v minus u over 2 times a, which is 2a. From our mathematics, this is difference of two squares. So this is the same as v squared minus u squared. Of course, when you open brackets here, you end up with this expression. Divide that by 2a. That is going to be equal to s. And when we make this a flat equation by multiplying times 2a on both sides here, even here times 2a, we shall end up with the expression of 2as is equal to v squared minus u squared. When we make v squared the subject of the formula, we shall end up with v squared is equal to u squared plus 2as, which is our fourth equation of motion. Our fifth equation of motion, we shall still use the same technique by playing around with the first two equations of motion. Still, our first equation was v is equal to plus at, and then when we make u the subject of the formula, it's going to be v minus at. So we substitute this u, value of u, in the second equation of motion, which is u, that u there. So when we get this u and substitute it right there, it's going to become the value of u, we put v minus at in its place, plus v, divide that by 2. Of course, when you open brackets with the t multiplied through, vt minus at squared plus tv, divide that by 2, you end up with your real tv plus tv is equal to 2tv minus at squared, which is that, minus at squared, divide that by 2. And definitely we will end up with our final expression. Our final expression is going to be s is equal to tv minus a half at squared, and that's our fifth equation of motion. So again, throughout, these were the parameters we were considering: displacement, initial velocity, final velocity, acceleration, and time. And each of those equations we were trying to derive, all these equations we derived, you saw that our first two equations were the ones that we derived from scratch. The first one we derived using the definition of acceleration. The second one we derived using the concept that the area under the graph is equivalent to the distance traveled by that particle. And then all these other three equations of motion were derived by substituting these two. We substitute these two in such a way that we eliminate v, we eliminate t, and we eliminate u in these substitutions of these two equations to be able to attain these other three equations. Now that we finished deriving the equations of constant acceleration, we'll go ahead and do some mock examples. Right here we have a question: a body moves along a straight line from A to B with a uniform acceleration of 2/3 meters per second. So we are going to start straight away with summarizing this question. A body moves along a straight line from A to B. So if this is our straight line, it's moving from point A to point B. And in this straight line from point A to B, it's moving with a uniform acceleration. So the acceleration of this body is 2/3 meters per second. Of course, acceleration is meters per second squared. So meters per second squared. The time this thing is taking is 12 seconds. So the time taken here is 12 seconds. The velocity at B is 25 meters per second. So the final velocity, because it starts from A to go to B. So the velocity at A is what we shall be calling our initial velocity. It's not given in the question. The final velocity at B, which we shall call capital V, is 25 meters per second. Find the velocity at A. So we are being required to find the initial velocity at A. So to find the velocity at A, we shall use the first equation of motion. V is equal to u plus at. We have our final velocity as 25 meters per second, so 25 is going to be equal to the initial velocity u, which we are looking for, which is u plus the acceleration, which is 2/3, times the time taken from A to B, which is 12 seconds. And definitely when we make u the subject of the formula right there, we shall end up with our answer as 17 meters per second. That's our initial velocity, and that's part A answered. Now part B of the question requires us to find the distance AP. When it's moving from A to B, what is the distance? So to find the distance moved from point A to point B, we are going to use V squared is equal to, this is part B, V squared is equal to U squared plus 2AS. We'll use that equation of that formula. So our final velocity V here is 25. So this is going to become 25 squared is going to be the initial 17 squared plus 2 times acceleration. Now we have our acceleration as 2/3 meters per second. So times 2/3 times the distance. Now it is the distance we are looking for, the distance of AB. So the distance, we shall leave it as S. So of course this, when we make S the subject of the formula, this is going to end up in 25 squared minus 17 squared. We have shifted that 17 to come this way, is going to be equal to, here we remain with 2 times 2 is 4/3 times S. Now definitely this is going to result into, when we make S the subject of the formula, this is going to become 25 squared minus 17 squared, divide all that by 4 times 3. And definitely now our value of s, the distance between A and B, is going to end up being 252 meters. Now this is when we've used this. Now remember, we have up to 5 equations of motion, so it means that you can as well use any other as long as you see it will work for you. So part B can also be done in an alternative way. We've used this equation, we can also use this equation to get the distance. S is equal to ut plus a half at squared. Now the initial velocity u is 17. We got it here, so it's going to be 17 times the time. The time taken to move from here to here is 12 times 12 plus a half times the acceleration. The acceleration is 2 over 3 times time squared. 9 time is still 12 squared. And when we add all this up, you still end up with 252 meters. 252, just the same as this. So with part B, you can use this or you can use that formula. Either way, you will still be able to get the same answer. A cyclist travels downhill while accelerating uniformly at 1.5 or 1.5 meters per second squared. If the initial velocity at the top is that, find how far he travels in 8 seconds. Again, to summarize this question, he's accelerating at this, so meaning that the acceleration there is 1.5 meters per second squared, which is the same as saying 3 over 2 meters per second squared. That's the acceleration. If the initial velocity at the top is that, so meaning initial velocity is 3 meters per second, then find how far he travels in 8 seconds. So they want you to find the distance he travels when the time is 8 seconds. So how far he travels in 8 seconds. So now from our equations of motion, what we can use here, they want us to find the value of s. So if we use s is equal to ut plus a half at squared, so we want the value of s, so that's going to be u. Our initial velocity is 3 times time, which is 8, plus a half times our acceleration is 3 over 2 times time squared. Our value of t is 8, so it is 8 squared. And therefore when we sum all this up, we end up with 72 meters. So it means that in 8 seconds, this guy, the cyclist, will have traveled 72 meters, and that's our answer. Part B. So how far does he travel? Again, they're asking you how far does he travel. So they're asking for distance. How far does he travel before reaching a velocity of 7 meters per second? So what is the value of s when the final velocity v is 7 meters per second? So how far does he's going to travel? How far does he travel to reach this velocity, the final velocity? Remember, all this still, his initial velocity, according to the question, is 3 meters per second. So his initial velocity will still be 3 meters per second. And of course, he'll still be accelerating at the same level of 3 over 2 meters per second squared. That is according to the question. Now, of course, that he won't take the same time to reach this. So now still here, to get our value of s, we shall use v squared is equal to u squared plus 2as. That's going to be now our final velocity. There is 7 squared is going to be initial velocity, which is 3 squared plus 2 times the acceleration, which is 3 over 2 times the value of s we are looking for, which is that. So making s the subject of the formula here, s is going to become, this is 7 squared, this goes that way, it becomes minus 3 squared. That is, this 2 cancels with that 2. So all this is going to be divided by 3. So our value of s here becomes 40, because this is 49, minus 3 squared, which is 9. Divide that by 3, we get you 40. divide that by 3, and so our value of s is 13.33 meters. So this is the distance he travels, that is how far he travels before reaching the velocity of 7 meters per second. Now a body moves along a straight line uniformly, increasing in velocity from 2 meters to 18 meters. So we are looking at a body. This is the body. It is moving, let's say it's moving from point A to point B. But they're telling us that it's moving in a straight line, uniformly increasing in velocity from 2 meters per second. So meaning that at this point it is initial velocity where it starts from is going to be 2 meters per second. And it moves from that velocity to that velocity. So meaning that its final velocity v is going to be equal to 18 meters per second. And it is moving in a time interval of 10 seconds. So meaning that the time it's going to take is 10 seconds. There we will be being required to find the acceleration and the distance traveled. So here we are supposed to find the acceleration and the distance traveled. So again, from our equations of motion, to find the acceleration, we can just go on with the first equation of motion. To find the acceleration, we know that v is equal to u plus at. What is v? Our final velocity is 18. Is going to be initial velocity u, which is 2, plus our acceleration, which is a, times the time, which is 10 seconds. And then we shall end up having, when we're making a the subject of the formula, this 2 comes this side, it becomes 18 minus 2 is going to be equal to a times 10, which is 10a. Divide both sides by 10. So definitely this goes with that. You have your acceleration as 1.6. So therefore acceleration is 1.6 meters per second. That's the acceleration according to the answer. 1.6 meters per second. Now after finding our acceleration, we can now go ahead and find the distance traveled. And of course the distance traveled, which is s, this is part A. So to answer part B, the distance traveled s is going to give us be equal to ut plus a half at squared. Now our initial velocity u is 2 meters per second, so it is 2 times our value of t, which is 10, plus a half times our acceleration, which we got here as 1.6, times squared, our value of t is 10 squared is 100. So to get our value of s here, when we put all this, sum this all up, you get 100 meters, and that is our distance traveled from A to B. So a train starts from rest and accelerates uniformly at 1.5 meters per second until it attains that speed, a speed of 30 meters per second. Find the distance the train travels during the motion and then the time taken. So now the question says that a train starts from rest. Now when they say that a train is starting from rest, it means that its initial velocity u is equal to 0 because it's starting from rest. And it accelerates uniformly at 1.5 meters per second. So it means that its acceleration here is 1.5 meters per second squared until it attains a speed of 30 meters per second. So it accelerates until it attains a speed that's now this is the final velocity. So it attains a final velocity v of 30 meters per second. Find the distance the train travels during the motion. So you're required to find the distance the train travels during the motion and the time taken. So you also need to find the time taken. So to find our value of s, we can use the third one. V squared is equal to u squared plus 2as. Our value of v in this case is going to be 30, so it's going to be 30 squared is going to be equal to u squared. Our value of u is 0, so it's 0 squared plus 2 times acceleration, which is 1.5, times s, that is s width, what we're looking for. So 30 squared, which is 900, is going to be 0 squared, which is 0, plus 2 times 1.5, which is 3s. Divide both sides by 3. So our value of s is going to end up having 300 meters. So the distance the train travels during the motion is 300 meters. That's what we've got. So now to find the time taken. So still to find the time taken, we are going to use one of the equations of motion, one that is appropriate. So to find the time taken, we shall say S is equal to U plus V over 2, multiply that by T. We know our S is 300, so 300 is going to be equal to initial velocity, which is 0, plus final velocity V, which is 30, divide that by 2, and all this is multiplied by T. So that is going to give us 30 over 2, because 0 plus 30 is 30, so 30 over 2 is 15, so it's 15. T giving us 300, divide that by 15, divide that by 15. That goes with that by 15 once, by 15 is twice 0. So the time taken here is 20 seconds. So that's the time taken for the train to travel. So you can as well try out that number on your screen. The cheetah can accelerate from rest to 30 meters per second in a distance of 25 meters. Find the acceleration. I expect that the acceleration you'll be able to get is 18 meters per second squared. You could try it out. In this video, I'm going to explain the concept of retardation. We're going to plot a graph that is going to represent retardation. The other word for retardation is negative acceleration, or call it deceleration. Let's take a case in point. For example, a body starts moving. Its initial velocity at moving is 10 meters per second. Then it moves for 2 seconds, and after 2 seconds, its final velocity is 2 meters per second. It started from 10 meters per second to 2 meters per second. It would mean that its graph would look like this. So it means that 10 is its initial. It started from here, then it moved from 10. After 2 seconds of movement, its final velocity is 2. So its final velocity is right there, 2 meters per second. So that's the graph. It moved from 10 to 2. So if you have to look at that graph, this graph will give us a negative slope. By definition, we know that acceleration is the rate of change of velocity. When the rate of change of velocity is increasing, it means that the velocity time graph is going to give you a positive gradient. But if the rate of change of velocity is reducing, it means that you're going to have a retardation, or you're going to have deceleration. And this, since this is going to give us a negative slope, it means that it is negative acceleration. To get this acceleration, we know that by definition that acceleration is the rate of change of velocity. The rate of change of velocity means that you're going to look at the initial velocity here, which is 10, minus the final velocity, which is 2, divide that by the time. The initial time the initial time was 0, minus the final time was 2. And 10 minus 2 is definitely 8. You divide that by negative 2, and you end up with 8 divided by negative 2 is negative 4. Negative 4 meters per second squared is the acceleration. Now, of course, here we are having 8. The acceleration, this is the rate of change of velocity. Initial velocity minus final velocity gives us 8 in terms of meters per second. So it's meters per second. Divide that by 2. 2 is in time, is in seconds. Divide that by 2 seconds. So meters per second, divide that by second, gives us meters per second squared, and this is the unit for acceleration. Now this negative value, the negative acceleration, is signifying retardation. It is signifying that the rate of change of velocity with time is reducing. We have a stone. It slides across a horizontal sheet of ice in a straight line. We're going to first summarize this question with a diagram. We first summarize it diagrammatically, then we solve it. So the question says we have a stone. It slides across the horizontal sheet of ice. So let's look at this as a horizontal sheet of ice, and it passes point A. We are having here point A with a velocity of 14 meters per second. So it means that at this point, the velocity there is 14 meters per second. Let's call this our initial velocity because it starts from point A. It passes point A with a velocity of 14 meters per second. We shall call it our initial point. And then point B 2.5 seconds later. So meaning that it's going to pass point B. But from point A to point B, the question is telling us that it's going to pass there 2.5 seconds later. 2.5 seconds. So meaning that the time taken to move from A to B is 2.5 seconds later. Assuming uniform retardation. So meaning that they are telling us that the velocity here, by the time it reached at B, it reduced, meaning that the rate of change of velocity was reducing as the body was moving from A to B. So assuming that the retardation was uniform and the distance AB was 30, so meaning that our distance S, denoted by S, is 30 meters from A to B, they're asking us to find Roman 1, the retardation. So we are going to, so we have the distance S, we have the time, we have the initial velocity u. So from our equations of constant acceleration, we shall choose an equation that is going to help, that satisfies all these to give us our value of A. And since the body is retarding, we definitely expect our value of A to be negative. So we shall pick on the one that shows displacement, the displacement equation. S is going to be equal to ut plus a half at squared. And we know that our value of displacement S is 30 meters, so we have 30 meters is going to be equal to initial velocity, which is 14, times the time. It takes 2.5 seconds to move from here to that point B, which is 2.5, plus a half times the acceleration, it is what we are looking for, times t squared. Now the time is definitely times 2.5 squared. So when we make A the subject of the formula, we shall end up with a value of acceleration being negative 1.6 meters per second squared. Now this negative simply signifies that the body is undergoing a retardation or a deceleration, and so it means that our answer, we shall conclude by saying that the body retards at a rate of 1.6 meters per second squared. So we'll go ahead and do Roman 2. They want us to find the velocity at B, so we do not know the velocity at B. So we'll go ahead and calculate the velocity at B. Still, we're going to use one of our equations of motion to find the velocity at B. The velocity at B in this case will be, we shall use the velocity at B, VB. V is going to be equal to, we can use V squared is equal to U squared plus 2AS. This is part B we are answering. So this is going to become, our initial velocity is 14 meters per second, so it's 14 meters per second plus 2 times acceleration. Now our acceleration here is actually, it has a negative value. Remember, we got our acceleration as negative 1.6, so it means that in our value of area in our calculation, we have to respect that negative and put it there. It's negative 1.6 because it's actually a retardation. Negative 1.6, 2 times acceleration times S. Our value of S, which is the distance, is 30 meters times 30 meters. So it's 14 squared plus 2 times that times 30 meters. So definitely when you get this, you'll end up with 100. When you find the square root on both sides, you'll end up with your velocity as 10. So our velocity here is 10 meters per second. Third question is asking us, how long after passing A does the stone come to rest? So remember, this stone, when it started from here, it moved on from A at an initial velocity of 14 meters per second. As it kept moving, it reached point B, and the velocity we got at B was 10 meters per second. Now for it to come to rest, it means that it is supposed to continue until its velocity is 0. So it means that when they ask us for how long after passing A does the stone come to rest, they are actually asking us to find the time it's going to take for it to move from point A at that velocity up to a certain point when the velocity is 0. So it means that we are simply trying to find the value of time when the initial velocity is 14 and the final velocity is 0, because it is when the final velocity is 0 that the stone eventually comes to rest. So in our write-up, we shall assume, so we are trying to find a certain point, let's call it point C, and at this point the velocity is supposed to be 0, the final velocity. So we need to find the value of time. How long after passing A does the stone come to rest? So it comes to rest when the final velocity is V. So to calculate that also, we shall simply come and say V is equal to U plus acceleration times time. And so it means this is part C. So meaning the final velocity here is 0, is going to be equal to the initial velocity. Our initial velocity in this case is 14 meters per second, so it is 14 meters per second plus our acceleration, which is still decelerating at a rate of 1.6 times time. So we find the value of t. So this is going to mean when 14 comes here, it becomes negative 14, is going to give us negative 1.6 t. So after passing point A, the stone is going to travel for 8.75 seconds until it comes to rest. And it comes to rest when its final velocity is 0. This brings us to the end of this video. Thanks for watching. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.